Okay, so on to Chapter 5. Linear transformations is the topic for today. We're going to make it probably about halfway through this section, something like that. Maybe a third. So this is something we have not defined up to now, but it's something that we've actually made pretty significant use of. We've actually dealt with several linear transformations so far. We just haven't used the word yet. So let me tell you where a couple of those linear transformations have been. Remember, very early on, we talked about how you can interpret a matrix as a function, right? And this allowed me to make certain interpretations about determinant, geometric interpretations about determinant, which is neat stuff. That is actually a linear transformation. We just didn't use that term. Then we talked about multilinearity. And the big idea with multilinearity is that if you look at determinant sort of one row at a time, the whole rest of the matrix is being fixed, and just focus on one row and how as you change that one row, then you get changes in the value of the determinant. That thought of in that way, determinant is linear in each row. So another way to say that is that function, interpreting determinant as a function of a single row, is a linear transformation. I didn't use the term at the time, right? We talked about linearity there. And then also, when we talked about linear differential equations, we talked about L as being a linear operator, right? And we talked about what that meant, and I'm going to delay reminding you all of that just at the moment. But that also is a linear transformation. Okay, so I'm just going to now finally get around to defining what a linear transformation is. Before we do, I want to remind you all of some terminology about functions. A function you can think of as a process or a mapping, different ways to think about it. But I like to think of it as something that takes an input and takes it over into this other world and sets it down somewhere as an output. Right? Okay. So, with that point of view in mind, the space that the inputs come from is called the domain. We need to be able to talk about this space. The way we talk about things is giving them names. So this is called the domain. This world over here that the outputs land in is called the target. You may have heard different names for this. I want to use the term target in this class, and I'll say a little bit more about that in a minute. Okay. So domain and target. And so a notation I want you all to be aware of is give the function a name, call it f. You say colon. The colon says I'm going to tell you some important features of this function f. Domain, and then an arrow, and then the target. And in fact, really, when you're talking about a function, if you want to be really precise about it, a function is actually the trio. A lot of people think of a function as just being a formula. Really, we need a little bit more than that. A function is a domain and a target and a formula that tells you how to get from the domain into the target. Okay, so it's the trio itself. Okay, now there is another set that we need to talk about, and that is, you'll notice here that the way I have this function drawn looks like all those outputs from the function f, they all land inside the target, but it looks like they land inside of a smaller proper subset of the target, right? So there is this separate set to be considered, which is the set of all of the actual outputs. Now notice, nowhere when I wrote down what the target is, nowhere is it suggested that the target has to, that the outputs from the function have to actually fill up the entire target. Right? There's no such requirement. The target is just a world that the outputs have to land in. And the actual outputs, the set of all of the actual outputs from the function, not necessarily the same set.
Okay, so we're going to give that set a name as well, and I want to use the term image. Okay, so these are three sets that are importantly related to functions. These are the terms that I want to use. And now let me tell you some terms that I don't like. Well, one in particular term that I don't like, and I'm going to highlight this in red, the term range. And the reason I don't like this term range to refer to the image is that in some books, the term range also refers to the target. And this is bad, right? That's not good. To use the same word, right, to refer to two very importantly different things. Clearly different things, anyway. All right. Now, why did they do this? Well, I think that there are a lot of books where, and maybe it's because of the, what their needs are in that particular circumstance, or for whatever reason, they just don't feel the need to distinguish between the image and the target. Who cares? What does it matter? And so they said, whatever, the word range will just, it means whichever one, and doesn't really matter anyway, so who cares, right? So unfortunately, there is confusion as a result as to what this word means. So my solution to this is to just avoid the term, right? When I'm talking to someone about a function, if I say range, I don't really know for sure how they're going to interpret what I mean when I say that. And I don't want to say something that I think, if I think there's a reasonable chance I'm going to be misinterpreted, well, that's not good, right? So I just avoid the term completely. And likewise, flip side, if someone tells me, here's a function, and by the way, the range, blah, blah, blah. Okay, well, they said range. Now I've got to ask them to clarify. I'm sorry, which do you mean the target? Do you mean the image? Right? Because I want to know what they're talking about. Sometimes you can figure it out from context, but still. So anyway, in Math 216, let's try to avoid that word as much as possible because of this ambiguity. Now, there is another word that you can use for target. That word is codomain. That's fine. It just seems like it's not clear why I would say that when I could just say target. Right? All else being equal, target's a little bit friendlier, I guess. I just kind of like the term target better. Okay. Pause. Questions? Anybody? Everybody on board? All right. Okay, a couple of quickie examples. First, I want to show you an example where the image and the target are different. This is an easy example from single variable calculus. You don't even really need calculus for this, but here's a function from R1 to R1. So notice the domain is R1. That means this function is defined for all real numbers. The target is R1. What I'm saying by this is that as I describe this function, I'm saying that what comes out of this function will be a real number. And notice all this is confirmed by the formula, right? You can put any real number in to this formula. And what comes out of this formula will, in fact, always be then a real number. So, cool. But let's talk about the actual set of outputs. I mean, what really comes out of here? If you put real numbers in, and only real numbers in, notice that what actually comes out is not the same as the target. The target is the collection of all real numbers. The image, the actual outputs, are just the non-negative ones. So clearly different sets. So next example I want to show you is just to sort of explain why we would care about this difference. A lot of students will look at this example and say, okay, well, fine. So look, the image, the actual outputs here are just the non-negative numbers. Then what's the purpose of having this R1, this target? Why don't I just say phooey on that and let's just look at the actual outputs. We have actual inputs, actual outputs. Let's just call the image the target. Why don't we just do that? Right? The answer is sometimes it's pretty hard to figure out what the actual image is. For example, let's look at this function here. Right? Let's look at the output values there. What are all the outputs that come out of this function? And think about what the shape of this thing looks like, and you see there's an x to the fourth and a y to the fourth term. So in some sense, it's going up, the graph is going to be going up in all directions, and so this is not going to approach negative infinity in any direction. But how low does it go? Like what's the minimum value of this? Oh my gosh. Right? If I wanted to find the minimum value, I'd have to, take the gradient, set it equal to 0, but the gradient's going to have cubic equations in it. Now I'm solving a system of cubics. This is hard, right? And very often, completely irrelevant to what I'm doing, right? It might be that the only reason I'm talking about this function is that I want to know how maybe a certain directional derivative. Perhaps. Something like that. And in order to be able to talk about the function there, I just want to be able to say, look, 2 variables in, 1 variable out. And now let's do calculus. And I don't want to be bothered with finding out what the actual minimum value is and therefore figuring out the actual image. I don't need to know the image. I just need to know what kind of critters come out of this function. Right? So the concept of the target is very convenient. It absolves us from figuring out the image that I just don't need. Okay. Okie dokie. All right. So all of this terminology having been said, let me now tell you what a linear transformation is. This is just a definition. Here we go. A linear transformation is a function. Hopefully no surprise. There's 3 big requirements. First big requirement, the domain for this function needs to be a vector space. Y'all remember vector spaces. Second big requirement, the target needs to be a vector space also. And then the third big requirement, and this is the linearity condition, this right here. I hope this looks familiar, but when we talked about linearity in the context of multilinearity, when we talked about linearity in the context of linear differential equations, this function, our linearity condition for a function is that when you put a linear combination in, you should get the corresponding linear combination out. Right? So just like the way we used the term linearity in previous contexts. Right. How we doing? We okay? So really, the definition I'm making here of linear transformation is pretty darn familiar, right? It's just, that whole linearity thing. Oh, and side note, quick little asterisk. I need my domain and target to be vector spaces. That's it. Okay. All right. So it turns out that this is a very powerful concept. We're going to do some great things with this over the next few days, next few lectures. But before we do, a couple little details that we have to pound out. Some exercises for y'all to think about. If a function satisfies this condition, it must also satisfy this condition. So, if a function, linear combination in, linear combination out for linear combinations of 2 vectors, then it will also do the same thing for linear combinations of any numbers of vectors. And that's not hard to argue this. The big idea is to point out that, roughly speaking, the point is that you just apply this property n minus 1 times. Right? So in other words, you interpret this linear combination, this larger linear combination as, at first, 1 vector plus a second vector, that's all the others, right? And then take it from there. Right? So applying the above condition in minus 1. So it'd be a nice exercise, details for you all to pound out, but notice that if you use the purple condition, you can prove the green condition, and of course vice versa. Just let it n equal 2. And then another equivalent formulation. Some books will make this the definition. Adding inputs adds the outputs.
scaling input scales the outputs. Now, so there's two conditions here. You gotta make two separate requirements. That's clunkier in a way, but it's also, at least in some ways, it kind of looks easier because here it's just addition. You add the inputs, you add the outputs, right? You can really see what's going on there, and just one operation here as well. You scale the input, you scale the output. So there's an appeal. You might think of it as this is two easier conditions, perhaps, right? Compared to one, take your pick of the others, harder condition. So it's up to you which one you like to use. Depends on the circumstance. For me, I tend to gravitate toward this one. I think probably all else being equal, a little bit less pencil lead when you use that one condition, but take a choice. Okay, and then a little bit of lingo. This condition. You'll hear people use the following term quite a bit. People say that a linear transformation commutes with linear combinations. Y'all remember, I hope, this term commutes. Commute suggests, in a different usage, of course, but that you can kind of go in either order. It doesn't matter which order. You could do this one first and then that one, or go this one first and then that one, whatever. It doesn't make any difference. And that's kind of what's happening here. When we say commutes with linear combinations, note first we're doing the linear combination, and then secondly we're applying the linear transformation. That's on the left side, right? On the other hand, on this side, we're applying the linear transformation first, and then we're doing the linear combination second. So it's smacks of commuting, right? It's a little bit of an abuse of the term, but it's rolls off the tongue so nicely that people will still use this. Okay, so this is what people mean when they say commutes with linear combinations. Okay. Alrighty. I want to say a little bit more about semantics. There are usages of the term linear that are very convenient, but arguably a little sloppy. But again, so convenient, and people know what you mean when you say certain things. And so I just want to make you all aware of these. The side note: this page of notes was motivated by a conversation that I had with the Math 353. I'll say instructor, the instructor who's taught that course more than anybody else in the last 20 years. He made me aware that a lot of students get into Math 353 and they know what a linear transformation is, but he finds that when he uses the term linear, kind of casually, and as is going to happen a lot, by the way, in Math 353, lots of occurrences of this idea of linearity, right? That in his sort of casual uses of the notion of linearity in that course, that students like, I don't know what you mean. Linearly, what are you talking about? Right? So I just want to point out several instances of the kind of thing that you'll see and how that you're supposed to interpret those when they come up. So here's a phrase that you will hear said sometimes. A matrix acts linearly on vectors by left multiplication. Okay, so acts linearly. Here's what you should interpret when you see something like this. When you see the term linear, in really any context, if you see the term linear, first step is to identify, okay, in this sentence, there is some sort of a function being referred to. Step one, identify what is the function that's being referred to here. So, A acts linearly by left multiplication. Oh, well, this says we're taking vectors and multiplying them by this matrix A on the left. Okay, so here's the function.
Right? The function that's being discussed is the function that takes x as an input and gives ax as an output. This is this function that we talked about in chapter 1. This is t of x equals ax. I think I missed the, there we go. Okay, so that's this function right here. So step 1, identify what is the function being referred to. Step 2, interpret from the usage of the term linear that the speaker is describing this function as being a linear transformation. Right? So that's all that is being said here. You know, if we say matrices act linearly, and by the way, it'll sometimes be that succinct. People will say, you know, a matrix acts linearly. Okay, a matrix acts linearly. What do matrices do? Matrices, oh yeah, what matrices do is we can multiply them by vectors. Oh, that must be the function we're talking about. So when they say the matrix acts linearly, they're saying that this function is a linear transformation, and then you know what they're saying, and then you can go to the point of confirming, you know, wait a second, is that true? Is this a linear transformation? Etc. Okay. How are we doing? Everybody okay? I've just got several more examples of the same kind of sort of interpretation. You know, just interpret in this way. So here's one, a common phrasing people will make, that it's linear to map points in R3 to their nearest points in this following plane through the origin. So, you know, given a plane P, we talk about mapping points in R3 to the nearest point in the plane. Maybe you say, you know, projecting points to that plane. This is a linear map, or sometimes people say this is a linear projection. Okay, so step 1 in understanding what do they mean when they say that. Step 1 is identify where's the function. Where is something was here and then something happened to it and we got an output? And the answer is the projection is the function. So the usage of the word linear suggests that this projection, where x is the input and the projection is the output, that projection is a linear transformation. So it's just a lot easier to say linear projection than it is to say the function that takes as its input a point and then gives as its output the point on the plane that's nearest, you know, orthogonal, blah, blah, is a linear transformation. It's just a lot of words to say, and so these kinds of terminology can be really convenient. Okay, next example. Such and such is a linear operator described by this. Okay, what do we mean by linear operator? Well, there's that word, linear. Step 1, when you see the word linear, identify what is the function. Here's the function. We're given the function. The function takes that as an input and gives this as an output. Don't worry about this notation for just a moment. We have a function that's given to us. This is one of those chapter 4, you know, L kind of functions, right? L of f is something like this. Right? We talked about in chapter 4 about how the left side of a differential equation can be thought of as a function that acts on functions. Okay. So there's a function that's being described in this sentence. The usage of the term linear suggests that this function is a linear transformation. That's all they're saying here. Now, a side note, let's talk about the notation. We have never seen this notation before. No problem. This notation is something we'll talk about later on. I guess it'll be Friday that we'll get to talking about this. And I'll explain the motivation for it at that time. But for the moment, we're not asking you to understand everything there is to understand about this notation. I want you to understand what I mean when I say that this is a linear transformation. Okay. Lastly, old example, chapter 1, way back when, we described this as a linear system of equations. right? So what's the deal with the term linear there? This actually falls into the same category. There is a function in play here. The function is that if you have some input values x1 through xn, right? The whole business on the left-hand side turns that into this. You can think about this different ways. You can think about this as, well, that's just what the left-hand side does. You can think about this as, well, I can think of this as I'm multiplying this purple vector by some matrix with elements being the coefficients there. Take a pick, whatever, doesn't matter. But that's a function. X's go in, all this business comes out. That's a function. And by saying that this is a linear system that results, really what we're saying is that the function that creates the system in the first place is a linear transformation. Okay, so heads up about the lingo. There's a lot of sort of convenience, I'm going to say sloppiness, in the usage of that term, and just be aware that that's all it means. Okay, so let me show you an example of how to confirm something is a linear transformation. This is a brute force calculation. It actually doesn't take that long. This is it's just a little tedium, to be honest. But here's a function, R2 to R2, defined by that formula. I claim this is a linear transformation. I'm going to prove it for you. Keep in mind the way you prove something's a linear transformation is you check the linearity condition. Okay, we're also supposed to confirm that the domain and the target are vector spaces. That's super quick. Domain and target, both R2, clearly vector spaces. Okay, so to check the linearity condition here, all we're going to do is we're going to put a linear combination in and confirm that we get the expected linear combination out. So notice, linear combination in, same linear combination out. And everything else is algebra, right? It's just plug and chug. But let's walk through that. At least a little bit of it, as time permits. This vector x has coordinates, x1 has coordinates, x2 has coordinates. Let's just write it down in coordinates. I sort of need it in coordinates because the function is defined in terms of coordinates. Let's multiply out that linear combination in coordinates. I haven't really done anything yet. I'm just rewriting my input vector by coordinates. Let's plug into the function. Now here we got to be careful. That first entry, that's the x. So that's what goes there and there in my answer, in my output. The second entry that goes in, that's what in the formula is being used for y. So there and there, like that. And then notice all I've done is take this expression and just write down what it is. We know the given first input, given second input. That's what the function is. Everybody good? Okay. So having done that, it's just a matter of kind of moving terms around. But if I take all of the terms that have A's in them, you might think of it as, and kind of shove them all over here toward the left. And if I take all the terms that have B's in them and sort of shove them over here toward the right, that's just shuffling. I haven't really done anything, right? And then write this as a sum of two vectors. Pull out the common factor of A from all of these terms. Pull out the common factor of B from all of those terms. All right? And then I realize, having done that is T of x1, and this is T of x2, And as required, I mean, this, again, all I did is kind of multiply all out and confirm, but as required, linear combination in gives me the required linear combination out. Okay, all right, good stopping point. See y'all later. Have a good Monday.